Hey everyone, this time I want to take a look at an impulse question having to do with stopping at a red light. Okay. And you all have ridden in the car with someone or drive yourself. You know there's two ways of stopping. The normal way, where you see a red light and you start to slow down gradually. And then you've got those people who think they're going to somehow beat the red light. They go as fast as possible, wait till the last second, and then realize the red light's not going to change just because they're there, and then have to slam on the brakes. So we're going to look at the physics behind that. Okay. So first thing I'm going to do is I'm going to read the question. We're going to underline the things we've got going on. I'm going to draw the problem out, and we'll solve for what we want to look for. Okay. So Evgenia, okay, just some random name here, driving her 1,000-kilogram car. Okay, that's a mass at 12 meters per second. So we've got our velocity, mass, velocity. It's going to be our initial, right? If it says it, if the question starts out with saying, hey, it's doing this, that will be our initial condition. Okay. And ignores the red light ahead of her until the last second possible. If she stops the car in 2 seconds, we've got a time. What force is exerted on the car to get it to stop? Okay, so here we are looking for force. Okay? And so my drawing skills are awful. I'm very sorry, but we're going to give it a shot here. And so we've got initial system. We've got, some, hopefully your car doesn't look like this, but we've got some car moving. It's 1,000 kilograms. Velocity of 12 meters per second. Then after some time, we have the car stopped. Okay, right? So, okay, that is our final velocity, of course. Sorry, I missed that the first time around. Okay, so our final situation is, oh wow, guys, there's a reason I'm a science teacher, not an artist, but here we are. Okay, so the car is still at 1,000 kilograms, and our velocity is now 0 meters per second, of course. Oh, see, drawing that out made me even notice I forget to note that, hey, I do have the final velocity. This will help prevent you from getting into that situation of, where's this at? Where's that at? Well, I drew the situation out, realized I was missing one of the two things I cared about, and found it back up here. Okay? We can say that this duration here in between starting and stopping is 2 seconds. Oops. 2 seconds. Now I've got everything drawn out. Okay. We can list off what we've got now. We've got our initial velocity and our mass. Okay. Initial velocity. There's all kinds of different ways of doing it. I just need to see that you know the difference between the final and initial situations. My mass in the final one is still 1,000 kilograms. My final velocity is 0 meters per second. Okay, and so now we're trying to look for how we get there. Now, if I'm slowing down, my velocity is changing, and so we're looking at impulse, of course. And as we know by now, our impulse is the change in momentum. And as we are not changing the mass of the car, that change in momentum is just going to be the same mass of the car multiplied by our change in velocity, which will also be equal to the force over a given time, because that is how you change momentum. Right? And so we have our mass. We can get our change in velocity. We have our time. And then we're looking here for our force. So we just plug things in and we can end up with the answer, of course. Okay. So if we've got 1,000 kilograms, I don't want to do this in red, that's going to be awful. So we're looking for this. Let's do it in black. Okay, so we've got 1,000 kilograms times my change in velocity, which is equal to my final 0 meters per second, times subtracted from my initial 12 meters per second, equals my force, which is what we're looking for, times 2 seconds, of course. Okay. And so 0 minus 12 is negative 12. Negative 12 times 1,000, we've got negative 12,000 kilograms meters per second equals force times 2 seconds. Divide both sides by 2 seconds. 2 seconds. And this will give us force equals negative 6,000 newtons. Okay, the negative being backwards. And so what I would actually do myself is say, hey, 6,000 newtons opposite motion, or because we have our car going to the right there, to the left. Okay. 6,000 newtons is quite a bit, by the way. Okay. So we can compare this to if instead of stopping in 2 seconds, they're going to stop at just 6 seconds. Okay, So to put this in perspective for you, 12 meters per second is about 40 kilometers an hour. Okay. Now, again, we can draw all this stuff. This situation here is all the same. The only difference this time now is our time is equal to 6 seconds. Okay. The entire situation other than that is identical. Okay, so I'm not going to take the time right now to show you how to draw it all out again. And then we solve it just the way we did. Okay, and so using all of that knowledge up there, we're going to do 1,000 kilograms times 0 minus 12 meters per second equals 4 times 6 seconds. And you do the same math, but then instead this time you're going to get negative 12,000 divided by 6 and not 2. And so your force will be 2,000 newtons. Okay? To the left again. So by driving in a conservative manner, you can decrease your force by 2/3. Okay? And that's why it's more pleasant to ride with someone who brakes ahead of time and not at the end. Okay? There is one thing I do want to point out. As our impulse is equal to mass times change in velocity, okay? These between the two situations stayed constant, right? Okay? Those were the same because it's the same mass and the same change in velocity. That's not what actually changes. No matter what happens in that situation, the impulse is the same. Okay? But as we increased our time here, our force decreased. They increase and decrease proportionally, and so they're gonna. What that means is for the factor that time will increase, force will decrease by the same factor, and so our impulse actually remains the same. Okay. As always, everyone, have fun and good luck.